भाई घर वाला பேசுமா
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everybody. Most respected head of the Department of Chemistry, dear colleagues, and dear participants. I take this opportunity to congratulate the HOD of the PG and Research Department of Chemistry for organizing and conducting a webinar entitled Nomenclature of Chiral Complexes for the benefit of the students community. These are all the opportunities given by the department for the students to learn more than the curriculum which we are normally teaching in the classes. So I request all the participants to make use of the opportunity which has been extended to you to learn more and indeed all these other aspects which will be helpful for you in future endeavors. I congratulate all the people who are involved in this webinar, and I wish that this webinar will be a grand and great success for all the participants. Thanks for the opportunity given.
Assalamu alaikum. Good morning. Well, I thank the Almighty for giving me the chance. I thank our beloved principal and my colleagues for this webinar. I invite all the student participants and faculty from our college and other neighboring colleges for this webinar. Today's topic is chirality and nomenclature of chiral complexes. So chirality means handedness.
आता नहीं ऑन करना मेरा माइक
Chirality means handedness. What is the importance of this study? This study is very important in chemistry, particularly in organic and inorganic complex synthesis, because chiral complexes are enantiomers, maybe chiral complexes, and we all know that the enantiomers, the isomers, different isomers have different activity in medicine and all. So for the synthesis of for the synthesis of particular isomeric forms, the study of chirality is very important. Let us discuss in detail about chiral complexes. What is chirality? So it is any geometrical figure or group of points chiral and it has chirality if its image in a mirror plane ideally realized cannot be brought to coincide with itself. It is the object and its mirror image are not superimposable. Okay, for example, we have lactic acid. We have studied from our plus two. Lactic acid, the object and mirror image of lactic acid are not superimposable, and it has a asymmetric carbon. In organic chemistry, we see if the molecule has asymmetric carbon, may exist in chiral forms. So actually, chirality, the word chirality comes from Greek. It means hand. So chirality means handedness. You can see our hand. You take the right hand and keep it near the mirror, then the mirror will reflect the left hand. Now, if you try to superimpose these two objects, or you take your right hand and left hand, and if you try to superimpose, it is not possible. So that is non-superimposability of the object and its mirror image, that is the chiral. So our hand is chiral. Similarly, if you take our left ear and right ear, though it looks similar, they are chiral. So many parts of our body, foot, all these parts, different parts of our body are chiral. And similarly, you might have noticed there are thousands or millions of leaves in a plant, a tree. No plant will match, no leaf will match with other. So it is chiral. So nature has created many objects in chiral form. For example, if you take a chair, you see it is given, it is shown, and its mirror image will be superimposable. So if it is superimposable, that is achiral, that is not chiral. So chirality means the non-superimposability of the object and mirror image. Okay, you understand? Molecule is chiral if its two mirror image forms are not superimposable upon one another. If molecule is chiral, if its two mirror image forms are superimposable. So chiral means the two mirror images are superimposable, just like the chair shown in the figure, and chiral means not superimposable of the object and mirror image as shown our handedness, left hand and right hand. A simple organic molecule, chiral molecule is lactic acid. You see, this is the structure of organic molecule lactic acid. You can notice the object and mirror image, and if you try to superimpose, it's not possible. So the simple organic molecule is lactic acid, contains a chiral carbon, so it is not superimposable. Okay, let us come to the complexes. What are chiral complexes? A complex that is not superimposable on its own mirror image is called chiral. The phenomena is called chirality. Just like our organic molecule lactic acid, you can have a inorganic complex if its object and mirror image are not superimposable. The complex is called chiral. You can see this one, this molecule, that is tris oxalato chromium 3 anion. You can see the object and its mirror image. If you try to superimpose one another, you can find they are not matching with one another. Some of the atoms will not match. So this is called non-superimposability or chirality. So this is the chiral complex. So we have similarly we have different chiral complexes. Let us see one by one. Chiral complexes, very important property of chiral complexes, that is the compounds containing asymmetric carbon in organic molecules. Similarly, in inorganic complexes is optical activity. So optically active, that is they exist in extrorotatory D isomer and levorotatory L isomer. A chiral molecule and its mirror image are called enantiomers. So if you have the isomers which are mirror images of one another are called enantiomers. The enantiomers are what? Isomers which are mirror images of one another are called enantiomers, and similarly isomers which are not mirror images are called diastereomers. So isomers which are mirror images are called enantiomers, and isomers which are not mirror images are called enantiomers. Here chiral complexes are optically active. The chiral molecule and its mirror image are called enantiomers because its mirror image. They rotate the plane of plane polarized light by equal amounts in opposite direction. Enantiomers, that is D and L isomers, are called enantiomers. What is difference in D and L enantiomers? Molecular formula is same. The spatial arrangement of atoms is different, and also very importantly, their optical rotation will be different. One will be rotating in the right direction, another will be rotating in the left direction. So they are equal amount, that is important. So the rotation is the opposite direction, but the amount of rotation is same. So now, what are the conditions for chirality? For a molecule to be chiral, it should not possess an improper rotation axis, that is SN axis. What is an SN axis? The rotation followed by reflection in a perpendicular plane. That is, you take a molecule, rotate it and reflect it in a perpendicular plane, and if you get the same molecule, then it is said to possess an improper rotation axis, that is called SN. So it should not possess an SN axis. The chiral molecule should not possess an SN axis. That is the one condition. And similarly, it should not belong to the point group tetrahedral or octahedral point group CD or OH. We have seen tetrahedral molecule is nickel tetrachloride, and we have a lot of octahedral molecules. So it should not belong to the point groups tetrahedral or octahedral. And similarly, DNH or DND, but DN is chiral. Molecules belonging to the above point groups tetrahedral, octahedral, DNH, and D3D are not chiral. It is achiral because they possess an SN axis. So the primary condition is absence of SN axis. S1 axis is mirror plane. S2 axis is center of inversion, 180-degree inversion. S1 axis 360 degree, 360 by 361, and S2 means 360 by 180. S2 axis center of inversion. This all you will know in detail in group theory subject. So let us not go in detail about these notations. So complexes which have mirror plane or center of inversion are chiral, hence optically inactive. So if it has mirror plane, that means it possesses an S1 axis, If it has center of inversion, it possesses an S2 axis. So these molecules are not chiral, they are chiral. As they are chiral, they will be optically inactive. They will be optically inactive. But molecules belonging to the point group Dn do not contain SN axis of symmetry, hence they are chiral and optically active. I have given the previous condition. DNH, DND are chiral, but DN is chiral. So DN do not contain SN axis of symmetry, hence they are chiral and optically inactive. Examples is chlorobromofluoromethane. So this molecule contains C1 axis and not tetrahedral TD. So it is chiral. Because in organic chemistry, we can easily understand all the four substituents of the carbon are different. And the four substituents are different, it is chiral. So similarly, here this molecule, as it contains four different substituents, it is chiral. Okay. So this is the conditions for chirality. So again, I repeat. So chirality means handedness, that is the right hand and left hand, like that. Our right hand is the mirror image of our left hand. Our left hand is the mirror image of our right hand, and they do not superimpose on one another. So therefore, these molecules are called chiral. And similarly, if you take a ball, volleyball, you take its mirror image, and both will be superimposed. So they are chiral. Okay. So a molecule is chiral if its object or mirror image are not superimposable. If they are superimposable, it is called achiral. Okay. So the best example is in organic chemistry. We have studied from the beginning in +2 lactic acid. Lactic acid contains four different substituents in the central carbon. So it is called chiral carbon or asymmetric carbon. All asymmetric molecules are chiral molecules. Now, in this inorganic chemistry, we are discussing about the chiral inorganic molecules. Here we don't have carbon substituents like that organic molecules, but we have different complexes, metal and ligands surrounded by metal. But what happens is their object and mirror image are not superimposable. They are called chiral. Okay. A complex that is not superimposable on its own mirror image is called chiral. Because I repeat, because this is a new topic, so you have to understand this thoroughly. Based on this only, we can go for other topics. So the phenomenon is called chirality. Molecule containing a chiral carbon exhibits chirality. So chiral molecules are optically active. Optical activity means, what is meant by optical activity? Optical activity means the property of a molecule to rotate the plane of plane polarized light is called optical activity. If it rotates to the right direction, it is called dextrorotatory. D isomer or plus sign is given. If it rotates to the left direction, it is called levo isomer or L isomer or minus sign is given. Okay. So a chiral molecule and its mirror image are called enantiomers. That is, I told you, isomers which are mirror images of one another are called enantiomers, and isomers which are not mirror images of one another are called diastereomers. So here we discuss enantiomers because the isomers which are mirror images. So the isomers and its mirror image, two molecules will be there. We rotate the plane of polarized light in opposite direction, but the quantity is same amount. It is a vector problem. The conditions for chirality is molecule should not possess an improper rotation axis, that is SN axis. SN axis, what is an SN axis? What is the operation of an SN axis? Take a molecule, rotate it, and then rotate it to a particular degree, for example 180 degree, and reflect it in a perpendicular plane. This is called rotation followed by reflection. This is called improper rotation axis, SN, SN axis. If now the object and the mirror image you have got are same, then it is said to possess an SN axis, then the molecule is not chiral. So the condition for chirality is it should not possess an improper axis. That is, after the improper axis operation, that is rotation followed by reflection in perpendicular plane, the object and the mirror image you have got should not superimpose on one another. So that is called chirality. The molecule is chiral. If it rotates, if it superimposes, it is said to possess SN axis, it should not contain for chirality. So the absence of SN axis is a condition for chirality. Should not belong to the point group tetrahedral TD or OH octahedral point group, or DNH or DND, but DN is chiral. Molecules belonging to the above point groups, that is tetrahedral, octahedral, DNH, D3D, are not chiral because they possess an SN axis will be there definitely. So S1 axis mean mirror plane, and S2 axis mean center of inversion. You are inverting to 180 degrees, so 360 by 182 S2 axis. Complexes which have mirror plane or center of inversion are chiral because if it contains mirror plane, it will have S1 axis. If it contains center of inversion, it will contain S2 axis. Okay, so they are chiral, hence they will be optically inert. So we are discussing about chirality. So absence of this SN axis, that is either center of inversion or mirror plane or any SN axis, the condition for chirality. But molecules belonging to the point group DN do not contain SN axis of symmetry. Hence they are chiral and optically active. For example, chlorofluorobromo, methane, CHBrClF is not C1, not TD. So hence it is chiral. It does not contain SN axis. Okay. Now coming to our particular topic of complexes. So now let us discuss one by one. First, let us take triskelate complexes of the type MAA3 plus. What is mean by the ligand AA? AA means it is a bidentate ligand. AA means both the donor atoms are same. So that's why it is called symmetric bidentate ligand. AA. For example, oxalic acid, COO minus COO minus. So both the donor atoms are oxygen. But similar, if you take ethylene diamine, it is also NH2, CH2, CH2, NH2 oxalic oxygen. But you take any amino acid as a ligand, then you will have one end NH2, another end oxygen, then it is called asymmetric ligand. So then we give the symbol AB. So now here oxalic acid, both the donor atoms are same oxygen, so it is given the symbol AA thrice. N plus the charge belong to D3. D3 means a D3 point group contains element E, element C31, C32 and 3C2. So D3 point group. They do not contain any SN axis of symmetry. The subgroups do not contain any SN axis of symmetry, hence they are chiral. So all the molecules containing of the formula MAA thrice. For example, tris oxalatochromium and tris ethylene diamine cobalt, tris oxalatoiron. So all this where you have the symmetric bidentate donor ligands, and there are 3 bidentate donor ligands. The molecule is chiral. The example is this one. You take this is O, this one O. Carbon C, double bond O, O. Both the oxygen atoms. And similarly, these two are the other oxygen atoms, and these two are the other oxygen. Now they form an octahedron. See, if you take it this as the x plane, x axis, and this is as the y axis, and this is the z axis. You can view the 3-dimensional arrangement. So this is in one plane, and this is in another plane, and these two are in another plane. Okay. So this is tris oxalatochromium. Now you take its mirror image. You put a mirror, and you will get a mirror image like this. So it is like this. Now if you bring this close to this one, so try to superimpose, it is not possible. Of course, this central, this is chromium metal atom, and these oxygen atoms may match, but not this carbon-carbon bond oxygen atoms, so they will not match. So they will not match. So this is called non-superimposability. If you bring it close here, they will not match. So this is called non-superimposability. And the molecule is said to possess chirality. The molecule will be chiral, and they act as an object and mirror image, and this will have optical rotation in different directions. This and this will have different direction optical rotation. Okay. And next, if you take this ethylene diamine molecule, you can consider cobalt tris ethylene diamine cobalt 3 ion. This is cobalt intermetal atom, and NH2 CH2 CH2 NH2 NH2 CH2 CH2 NH2 NH2 CH2 CH2 NH2. So this is the tris-chelate complex. Now this is also a asymmetric complex, just like we have seen AA type, because both the donor atoms are same, A and A. Here both the donor atoms are nitrogen and nitrogen, so they are same. Now if you put a mirror image, take a mirror image and try to bring both of them close together, that is one over the other, you match the cobalt atom of one molecule with another molecule. This cobalt atom and these NH2 groups may match, but not these rings, CH2 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 rings will not match. So this is called non-superimposability. The object and its mirror image are not superimposable. Okay, so if the molecule and its mirror image or the enantiomers are not superimposable on one another, then it is called the chiral molecule. Chiral molecule, and it possesses after. You can see this is one molecule and this is one molecule. Now you can see I have given the symbol. This is called plus, and this is minus. Why? I told you that enantiomers have optical rotation in opposite direction. This is dextrorotatory. This plus sign denotes dextrorotatory. That is, this molecule rotates the plane of plane polarized light in right direction, whereas this molecule rotates the plane of plane polarized in light in left direction. So they rotate the plane of plane polarized light in opposite direction. Okay, so this is the can, and now this will come afterwards. This is called delta isomer, and this is called lambda isomer. Just as the inorganic molecule we have RS notation, in inorganic also we give the absolute configuration of the molecule is given a symbol that we can understand. Now we can afterwards a little now. So this is about the complexes of the type MAA thrice. Now come to the triskeleate complexes of the type MAV thrice. MAV mean the donor atoms will be different. Donor atom will be different. For example, take glycine. One will be oxygen of the carbonate carboxylate group and COH group, carboxylic acid group, and another will be the amino group, NH2 group. So the donor atoms are oxygen and nitrogen. Similarly, if you take alanine, so amino acids contains two donor atoms. They are bidentate, but the donor atoms are not same. They are different. One will be oxygen always, and another will be nitrogen always. So they are asymmetric bidentate ligands. So they given the symbol AB. Here it can be oxygen and it can be nitrogen. MAB thrice, tris bidentate complexes. They belong to the C3 point group. They do not contain any SN axis of symmetry, hence they are also chiral. So the complexes, triskeleate complexes of the ligand, both the ligand symmetric bidentate as well as asymmetric bidentate are chiral. They do not contain SN axis of symmetry, hence they are chiral. Okay, so this is the case. So this is GLY means glycine, is given the short form symbol as abbreviated as GLY, glycine. ALA means alanine. S means S isomer. And similarly, the complexes of, so far we have seen triskeleate complexes. Now let us discuss about the biskeleate complexes, and the other two ligands are same. So CO, AA twice, L2 like that. So this is ethylene diamine symmetric chelate ligand, two symmetric chelate ligands, and two same ligands, monodentate same ligands. And here also oxalate symmetric chelate ligand, oxygen, and the monodentate same ligand. So these molecules are also chiral. They belong to the point group C2V point group. So here you see this is the structure. This is the structure. You have, for example, if this is COE and twice mean, this is the cobalt atom. This is the cobalt atom.
कंटिन्यू कर अब्दुल आपके
You just look at these molecules. You look at these molecules. What is the difference between this one and the previous these two? Just look at these molecules and understand what is the difference. This one and this one. In this molecule, all the donor atoms are same. In this case also all the donor atoms are same. Whereas here you have two bidentate ligands, so therefore the four donor atoms are same. In case of ethylene diamine, four nitrogen atoms and two chlorine atoms. So it is of the type COAA twice Cl2. It is a bis chelate complex and also two monodentate ligands. It is an octahedral complex. You can see these two are the chlorine atoms. These two are the chlorine atoms. Cl green color is given in green color, chlorine, fluorine, and these two are the nitrogen atoms of the ethylene diamine, and these two are the nitrogen atoms of the ethylene diamine group. So here, see this molecule. This is the object, and this is its mirror image. And if you try to bring it close together, they will not superimpose one another. Put this cobalt atom over this cobalt atom, they will not superimpose. You can see very easily the two chlorine atoms are this side, whereas if you try to superimpose, they will go to the opposite side. So they are not superimposable. This molecule contains a C2B point group. So it is chiral. It does not contain any SN axis. So it is chiral. Similarly, another inorganic molecule, though it is not a complex, it is simple inorganic molecule, hydrogen peroxide, H2O2. H2O2, skew form of H2O2. They are in a different plane. This hydrogen and this hydrogen are not in perpendicular plane. They are at different angles. Now this it belongs to the C2 point group. Hence it is chiral, but the isomers are short-lived, hence they are not separable. This is the object, and this is its mirror image, and these two are not superimposable. But the thing is, these isomers are not, they are very short-lived, lifetime is very short, cannot be separated. So as I already discussed, this COEN twice, you can write like this. If you cannot draw on paper like this. So simply you can draw it like this. This form you can easily draw. An octahedral skeleton and link these two by a ring. This is EN means short form of ethylene diamine. Instead of writing NH2CH2CH2 NH2, you can write like this. So these two are not superimposable. This is chiral. But if you take the transform of this one, this form is chiral, whereas the transform is not chiral. It contains a plane of symmetry. So the cis isomer is chiral, but not the trans isomer. Okay. Similarly, chromium EDTA. you have a synthesis a complex of ethylene diamine tetraacetic acid with chromium 3 ion. Chromium 3 ethylene. It is also chiral because this contains uh, this is a hexadentate ligand. Though it contains tetraacetic acid, 4 oxygen atoms of the carboxylate groups and 2 nitrogen. They are not superimposable. So this is a hexadentate ligand containing 4 nitrogen atoms and 4 oxygen atoms and 2 nitrogen atoms. It is also not superimposable, and its mirror image it is chiral, and it belongs to a C2B point group. Similarly, ruthenium bipyridyl complex, tris bipyridyl complex is also chiral. Here, as I told you, you see trans this ethylene diamine dichlorocomplex and trans this oxalato dichlorocomplex. They contain SN axis. It is a mirror plane 180 degree, and they are chiral. So this one, we take this is the mirror plane. What is a mirror plane? A plane which divides a molecule into two equal halves. So you can divide the two equal. If you put a mirror here, this part will be the mirror image of this part. So this contains a mirror plane. So the molecule is superimposable. That is contains S1 axis of symmetry. So it is chiral. So this is an example for a chiral complex. So you see the cis isomers are chiral, optically active. They do not contain SN axis, whereas the trans isomers are achiral. They contain SN axis. They are not optically inactive. So the chirality plays a vital role in determining the optical activity of the complexes. So similarly, diene. Diethylene triamine, this complex, there are 3 nitrogen atoms and 1 chlorine is there. This is also achiral because it contains S1 plane, S1 axis, that is mirror plane. The molecule can be cut into 2 equal half to the is mirror plane. This one, and similarly cis rhodium H COPR3. This is an organometallic compound. This also contains SN axis, and this is also chiral. Okay, so these are the examples of chiral molecules, and up to this we have seen these are the examples of chiral molecules, the example of achiral molecules. So asymmetry, what is meant by asymmetry and dissymmetry of molecules? Asymmetry means molecules containing only CN axis where n is equal to 1, that is C1, are called asymmetric. Examples M, A, B, C, D. It is all the 4 ligands of a tetrahedral complex are different, and M, A, B, C, D, E, F, all the 6 ligands of an octahedral complex are different. They are called asymmetric molecules. And dissymmetry means molecule possessing only CN axis where n is greater than 1. If n is equal to 1, it is asymmetric. If n is greater than 1, it is called dissymmetric, and no other elements of symmetry are called dissymmetric. So asymmetric and dissymmetric molecules contain are chiral. Both asymmetric and dissymmetric molecules are chiral and they are optically active. So a chiral molecule can be either asymmetric or dissymmetric. Molecules belonging to C1, C2, C3, D2 and D3 point groups do not contain any SN axis, so they are called chiral and optically active. So these molecules are also chiral and optically active. So now, so far we have seen what is meant by chiral molecules. So what is the condition for chirality? How they exist? The object and mirror image are superimposed, not superimposed. Okay, now let us discuss how to name these complexes. That is called nomenclature. What is meant by nomenclature? Nomenclature means how to name a compound. Organic compounds, there are millions and millions of compounds, organic, inorganic. So how to name them? So that method of naming a compound is called nomenclature. So now what is the method of, we have studied the IUPAC nomenclature of complex compounds. Similarly here, what is the nomenclature for chiral complexes? Here I told you that a chiral complex can have its object and its mirror image. That is two molecules. So now we have to name, we have to symbolize these two molecules. The absolute configuration of chiral complexes is given by the symbols delta and del. It's called delta, that is the triangle delta, and this is called del. Okay. So now the thing is, what is mean by absolute configuration? What is mean by absolute configuration? The three-dimensional arrangement of atoms. The arrangement of atoms in space is called absolute configuration. That is, if you see this molecule, take this one. It gives a three-dimensional arrangement of atoms of this molecule in space. Where it there? This is in the, if it is there in the x-axis. This is in the, if these two are in the x-axis, this will be y-axis, and this will be z-axis, and this will be between the x, y, x, z, and y, z plane. So it gives a three-dimensional arrangement of atoms in space. 3D, 3D arrangement of atoms. 3D we have seen. Three-dimensional arrangement of atoms in space is called absolute configuration. Delta, given the symbol delta, and the mirror image will be given the symbol del. Okay, delta and del. The octahedral molecule is viewed along the threefold rotational axis. The handedness of the helix found where the ligand is noted. If it forms a right-handed helix, is called the delta isomer, and if it forms a left-handed helix, it is called the del isomer. See here, you have to note molecule along the three-dimensional axis, 3D axis. So this is the three-dimensional axis. 3D axis, you note the molecule, and if it forms a right-handed helix, the rings, it goes here, then this side, and comes this side. So it forms a right-handed helix. Right-handed helix. If it forms a right-handed helix, is called delta isomer. Delta isomer. And if it forms a left-handed helix like this, then it is called a del isomer. You see this one. Helical structure of proteins you have studied. This is the right-handed helix. Something like the steps of a water tank. So you can have spiral steps. Right-handed helix. This is called delta isomer. And if it forms a left-handed helix, then it is called del isomer. Okay, so this is delta isomer, del isomer. So you see here, this is the octahedral structure. Now you come to these rings like this. Come here. So it forms a right-handed helix. Right-handed helix. Then it is called the right-handed helix. So it is called the delta isomer. So this isomer is delta isomer. Then if its mirror image will form a left-handed helix. Like this. So you start from here, and then here, then here, like this. It forms a left-handed helix. Then it is called the del isomer. So if one isomer is right-handed helix, forms a right-handed helix, its mirror image will form a opposite left-handed helix. The right-handed helix is given delta isomeric form, delta symbol. Then the left-handed helix will be given left L, del symbol. For example, consider the enantiomers of ethylene diamine, tris ethylene diamine cobalt 3 ion. This is tris ethylene diamine cobalt 3. Now we can see like this. So it forms a right-handed helix. So it is given the symbol delta, and its mirror image is like this, and it forms a symbol depicts the absolute configuration. This is an organic also we have plus minus symbol. And in addition to that, we have RS notation. So, so here, there the groups are given priority based, and if you go in left direction, it is called sinister S. So similarly, here if it forms right-handed helix, it is given the symbol delta, and if it forms the left-handed helix, it is given the symbol del. And how about this plus and minus? Here this is different. This is optical rotation. Minus means it is having a levorotatory action. It is rotating the light in left direction, plane polarized light in left direction, and this is rotating the plane polarized light in right direction. So there is no relation between the handedness of the helix and optical rotation. So actually this is the right-handed helix, delta symbol, but its optical activity is left-handedness. Whereas this is forming a left-handed helix, but its optical rotation is plus. So this is the exact nomenclature, complete nomenclature. Should be read as delta minus COEN tries 3 plus. This is del plus COEN tries 3 plus. So like this you have to read. So there is no relation between this. You should not think that always the delta isomer will be having minus sign left-handedness. Always the delta isomer will have plus, that is exploratory property, and the del isomer may have levorotatory property. So there is no relation between absolute configuration and optical rotation. Delta says about the absolute configuration. It is this helix, whether it forms right-handedness or left-handedness. This plus minus sign give about the optical rotation. How this molecule rotates the plane polarized light. Okay, so this is the nomenclature. This is the best example for inorganic chiral complex. Best example is COEN tries 3 plus, and this is how it is given the symbol. Right-handed helix, delta isomer, left-handed helix, del isomer. Okay. Example the absolute configuration of the two isomers of triethylene diamine. So this one you can write like this and draw like this. So it is like this. Okay. So this is about the chirality of the complex as a whole. Now, if you go in detail, what is the chirality of the ligand? Nomenclature of conformation of the chelate ring. Chelate ring is there. This is ethylene diamine ligand. N is here. NH2, CH2, and back we have one carbon that also contains two hydrogens, CH2, NH2, CH2, CH2, NH2. So now if you see these two NH2 groups, they are not on the same plane. They form a left-handedness, left side. Compare this one, they come to the left. And similarly, if you have take this one, they come to the right. So for consider the chelatering of the ligand pyridine, its gauge conformation is one. This is the gauge conformation. If it forms right-handed helix, is given the symbol DO. This is of the ligand. Forms the right-handed helix. It forms the right-handed helix. Is given the symbol DO. If it forms the left-handed helix, left side, it's called lambda. So this is the handedness of the ligand. This is the handedness of the complex acetal. Understand? So this is the complex. Complex forms a right-handed helix is given the symbol delta. The complex forms a left-handed helix is given the symbol del. Now here we are giving in detail, going in detail. How about the handedness of the ligand? The handedness of the ligand is right-handedness, comes to the right hand, then it is given the symbol DO. It comes to the left-handed, it forms a left-handed helix, it is given the symbol lambda. It is this one. How it forms. Either it comes in the left direction or right direction. If it comes in the right direction, it is given DO. If it comes in the left direction, it is given the symbol del. Okay. Now, to take a tris-chelate complex, we have two isomers with respect to configuration. One is delta isomer, another one is del isomer. Okay. This is for the complex. Now, out of the three ligands, all the three will be having this del configuration. Del. After this two, this is the, again repeat. Take these two isomers, delta and del. In the delta isomer, these three ligands are there. These three ligands may have left-handedness or right-handedness. The right-handedness is called DO. So all the three can be DO. Or all the three can be del. Come to this point here. All the three can be DO. This is del isomer. Then its opposite will be delta. Okay. Now if this is DO, then its opposite will be lambda. So all the three DO, all the three lambda. First to understand this one. So this is observed configuration. One is delta, another one is del. So all the three ligands will be DO forms. DO forms means this one. Having a right-handed helix. All the three can be lambda forms, forming a left-handed helix. Okay. This is one case. And what is the next choice? Take again the del isomer, and two will be forming a right-handed helix, and one will be left-handed helix. Do lambda. So it is do, its opposite will be lambda. So if there are two do, there are two lambda groups. Okay, two right-handed means here it will have two left-handed. One left-handed means here it will have one right-handed. So do lambda do. Similarly, the third form is another possibility. Of all the three, here you see there can be 2 dou, 1 lambda, and here can be 2 lambda, 1 dou. And finally, here it will come, all the 3 will be lambda, all the 3 will be 2. Right. So these are the 8 isomers possible. Now here, after these 8 isomers, so these 2 are called absolute configuration of the complex, and this is the individual handedness of the ligand. Okay, totally 8 forms are possible. Out of these 8 forms, the delta lambda form, all the triskelet ligands are in the lambda handedness, left-handedness is more stable than its opposite, del dodo form. This form is more stable than this form. This is due to the carbon, hydrogen, and HH interactions that we can see in next slide. You see, all the 3 are lambda forms. This ethylene diamine is lambda form, this ethylene diamine is lambda form, and this ethylene diamine is lambda. All the 3 are lambda forms. So it is called delta absolute configuration, where the individual ligands are lambda. Okay. Now this isomer is given another name. It is called, as they form a parallel group. The CC bonds are parallel, hence it is called LEL form, LEL, because the CC bonds are parallel to the principal axis molecule, C3 axis of the molecule. Then hence it is called parallel. Parallel short form is LEL, they have taken. Parallel form. The lambda form is LEL form. Whereas if you take the opposite of this one, delta lambda, opposite is del do. Del do. Then now here this CC bond is oblique, it is not parallel to the principal axis. It's not parallel to the principal axis. So it is called oblique, OBLIQUE, oblique form. Hence it is called ob isomer. As this is parallel, it is called LEL isomer, and the CC axis bond is oblique to the principal axis. It is called OB isomer, oblique isomer. Okay, so this is about the nomenclature of inorganic complexes with respect to the chirality of the ligand, a nomenclature of chiral complexes, and we have seen also the chirality due to the ligand also. Okay, so if you have any question, you can ask me now. It's not facial meridional. We'll discuss another. We have next PowerPoint that we will discuss later. If you have any questions, you can ask. Questions, please. Okay, if you have any questions later on, you can post it to my mail ID or post it in the WhatsApp group. I thank all the participants, the organizers, this technical team of our college, for this presentation. Thank you, Ananda.